Okay, Assalamualaikum and very good evening. All right. So we will continue our experiment number 3. Okay. So this experiment is all about enzyme. Okay. So I've already given you the watch the video. So the earliest video that I'm showing to you is already the process of our experiment today. Okay. Okay. From here there are several questions you have to answer. Okay. Number one. Substitute the solution in the video into the equation below. Okay, this number 1 until number 3. Question number 1 and number 2 refer to the video that you have to see. This one. Okay, awak kena tengok video ni, baru boleh jawab soalan nombor 1 dan 2. Alright. Okay, number 1, substitute the solution in the video into the equation below. Okay. And then number 2, state the function of Folin and CO-Cal2 in the video. Okay, and then you have to plot a graph, okay, about the enzymatic reactions. So let's say we have 1.0 ml of acetylcholine nitrase, okay, was react with the 2 ml of acetylcholine iodides, okay, and 2.0 ml of phosphate buffer was then being added in. Okay, these two solutions will be incubated for 10 minutes before you added 1.0 ml of acetic acids and 1.0 ml of dithio bisnitrobenzoic acids. Okay. So and then those all food mixture will be further incubated for 10 minutes. Okay, and then you have to put 1 ml of sample was placed in the cuvette for absorbent reading at the 405 nanometer. Okay. So please note the color on 505 nanometer. Okay. So mostly for 505 nanometer is represent okay. It's a violet in color, okay? So between 380 to 450 nanometer. Okay, so it lebih kurang warna macam violets, alright? So now using all data below, you have to plot the graph, okay? So it's 400 nanometer, you will get 0 choline micromolar. So 0.067, 0.05 until 0.729 to 0.8. So plot this graph, okay? And get the standard curve based on the data given. So you're given 3 marks. Okay, determine the activity of enzyme if the absorbent or enzymatically activity give a reading of 0.552. Okay, so daripada graph tu awak kena plot So plot 0.552 dan awak check berapa banyak micromolar yang awak dapat. Okay. And then last one, you have to calculate the specific enzyme activity if the total protein contained is 10 milligram per ml and the enzyme have been diluted 5 times before enzymatic reaction take place. So to answer this question, number 3, this C ni, we have a special formula. Okay, you can find it on the videos. Okay. Alright, that's all for experiment number 3. Is there any question before I open the video for you? Jadi soalan tak sebelum kita tengok video mengenai eksperimen nombor 3 ni?
Tak ada, sir. Tak ada, sir.
Alright. Tak ada Okay, kalau tak ada, kita sambung tengok video pula Alright. So and then after that, kalau ada soalan, bertanya saya. Alright. So I open the video now.
Proteases break peptide bonds. In the lab, it is often necessary to measure and/or compare the activity of proteases. Sigma's Universal Protease Activity Assay may be used as a standardized procedure to determine the activity of proteases, which is what we do during our quality control procedures. In this assay, casein acts as a substrate. When the protease we are testing digests casein, the amino acid tyrosine is liberated along with other amino acids and peptide fragments. Free tyrosine then reacts with Folin and Ceocaltheus phenol, or Folin's reagent, to produce a blue-colored chromophore, which is quantifiable and measured as an absorbance value on the spectrophotometer. The more tyrosine that is released from casein, the more the chromophores are generated and the stronger the activity of the protease. Absorbance values generated by the activity of the protease are compared to a standard curve, which is generated by reacting known quantities of tyrosine with the FC reagent to correlate changes in absorbance with the amount of tyrosine in micromoles. From the standard curve, the activity of protease samples can be determined in terms of units, which is the amount of micromoles of tyrosine equivalents released from casein per minute.
Hello, my name is Carrie Cup-Enyard, and I'm a scientist at our Sigma Aldrich DeKalb facility here in St. Louis, Missouri. Today, I will show you a universally applicable way to test protease activity. At Sigma Aldrich, we mainly use this assay in our quality control area to ensure that our protease has sufficient activity before we ship it directly to you at your lab.
Before beginning the assay, we need to make sure that the following reagents are correctly prepared. A 50 millimolar potassium phosphate buffer, pH 7.5. This solution is placed at 37 degrees Celsius prior to use. A 0.65% weight to volume casein solution prepared by mixing 6.5 milligrams to milliliters in 1 liter. The solution temperature is gradually increased with gentle stirring to 80 to 85 degrees Celsius for about 10 minutes until a homogeneous dispersion is achieved. It is very important not to boil the solution. The pH is then adjusted if necessary with sodium hydroxide and hydrochloric acid. A 110 millimolar trichloroacetic acid solution prepared by diluting a 6.1 normal stock 1:55 ratio with purified water. 0.5 millimolar Folin and Ceocaltheus, or Folin's phenol reagent, which is the solution that will react with tyrosine to generate a measurable color change that will be directly related to the activity of proteases. A 500 millimolar sodium carbonate solution prepared using 53 milligram to milliliter of anhydrous sodium carbonate in purified water. An enzyme diluent solution, which consists of 10 millimolar sodium acetate buffer with 5 millimolar calcium, pH 7.5 at 37 degrees Celsius. This solution is what we use to dissolve solid protease samples or dilute enzyme solutions. The L-tyrosine standard stock solution, which should be at an initial concentration of 1.1 millimolar. A 0.2 milligram to milliliter solution of L-tyrosine is prepared in purified water and heated gently until the tyrosine dissolves. As with the casein, do not boil this solution. Allow the L-tyrosine standard to cool to room temperature. This solution will be diluted further to make our standard curve. If necessary, a solid protease sample of predetermined activity, which is dissolved using enzyme diluent to 0.1 to 0.2 units per milliliter. This solution serves as a positive control for the quality control assay and as validation for the calculations we will perform to determine enzyme activity.
Now that we've prepared our reagents and they're all at the correct temperature, we will begin our protease assay.
To begin this assay, find suitable vials that will hold about 15 milliliters. For each enzyme that you will test, you will need 4 vials. 1 vial will be used as a blank, and 3 others will be used to assay activity of 3 dilutions of the protease. 3 dilutions are useful when checking our final calculations against each other. To each set of 4 vials, add 5 milliliters of our 0.65% casein solution and let them equilibrate in a water bath 37 degrees Celsius for about 5 minutes. Then, add varying concentrations of our enzyme solution to 3 of the test sample vials, but not the blank. Mix them by swirling and incubate for 37 degrees Celsius for exactly 10 minutes. The protease activity and consequential liberation of tyrosine during this incubation time is what will be measured and compared between our test samples. After this 10-minute incubation, add the 5 milliliters of the TCA reagent to each tube. Then an appropriate volume of enzyme solution is added to each tube, even the blank, so that the final volume of enzyme solution in each tube is 1 milliliter. This is done to account for the absorbance value of the enzyme itself. Now incubate the solutions at 37 degrees Celsius for 30 minutes. During this 30-minute incubation, you may want to set up your tyrosine standard dilutions, which is done using 6-gram vials that can easily hold 8 milliliters. To the 6 vials, the 1.1 millimolar tyrosine standard stock solutions is added with the following volumes in milliliters: 0.05, 0.1, 0.2, 0.4, and 0.5. Not add any tyrosine standard to the blank. Lower standards may be needed for impure test samples that will yield little color change. Once the tyrosine standard solution has been added, add an appropriate volume of purified water to each of the standards to bring the volume to 2 milliliters. For each of the test solutions and the blank using a 0.45 micron syringe filter, 2 milliliters of the test samples and blank filtrate is then added to 4-gram vials that can hold at least 8 milliliters. You can use the same type of vial in which the standards were prepared. All of the vials containing the standards and standard blank, 5 milliliters of sodium carbonate is added, and for best results, the Fallon's reagent is added immediately afterwards. Sodium carbonate is then added to our test samples and test blank. You'll notice that these solutions become cloudy after the addition of sodium carbonate. Then, the Fallon's reagent is added, which will react with free tyrosine. Gram vials are then mixed by swirling and incubated at 37 degrees Celsius for 30 minutes. After this incubation, you should notice that the standards have a gradation of color correlating with the amount of tyrosine added, the highest concentrations of tyrosine appearing darkest. You can also notice appreciable color change in our test samples. 2 milliliters of these solutions are filtered using a 0.45 micron syringe filter into suitable cuvettes.
Now that we've finished our assay, let's proceed to the spectrophotometer and record our absorbance values.
Absorbance of our samples is measured by a spectrophotometer using a wavelength of 660 nanometers. The light path is set to 1 centimeter. Record the absorbance values for the standards, standard blank, the different test samples, and test blank. Once all of the data has been collected, we are ready to create our standard curve. In order to generate the curve, difference in absorbance between the standard and standard blank must be calculated. This is the absorbance value attributable to the amount of tyrosine in the standard solutions. After this simple calculation, we create our standard curve by plotting the change in absorbance of our standards on the y-axis versus the amount in micromoles for each of our 5 standards on the x-axis. We have entered in our data points, generate a best fit line. And find the change in absorbance in our test samples by calculating the difference between our test sample absorbance and the absorbance of our test blank. Looking at our standard curve, we identify the absorbance value for one of our test samples on the y-axis. Now, traveling parallel to the x-axis, we draw a line and stop at the point where we hit our standard curve. Then, from the x-coordinate taken at this point, we have the amount in micromoles of tyrosine liberated during this particular proteolytic reaction. The activity of enzyme in units per milliliter, perform the following calculation. Take the number of micromoles tyrosine equivalents released obtained from the standard curve and multiply it by the total volume of the assay in milliliters, which in our case is 11 milliliters. Then, divide this value by 3 other quantities. time of the assay, which we ran for 10 minutes. The volume of enzyme used in the assay, which was varied. Let's use 1 milliliter. The volume of milliliters used in colorimetric detection, which may differ based on your cuvette. We use 2 milliliters. Micromoles of tyrosine divided by time in minutes gives us our measurement of protease activity that we call units. Cancel out the units for volume measurement in the numerator and denominator and are hence left with a measurement of enzyme activity in terms of units per milliliter. To determine the activity in a solid protease sample diluted in enzyme diluent, we divide our activity in units per milliliter by the concentration of solid used in this assay, originally in milligram per milliliter, leaving us with activity in terms of units per milligram. We've just shown you how to analyze protease activity using Sigma's universal protease activity assay. As you have seen, when doing this procedure, it's paramount to remember to heat both the casein and tyrosine solutions slowly and not to boil them. Also, it's critical to prepare different blanks for both your standards and for each test sample that you have.
So that's it. Thanks for watching and good luck with your protease activities.
Okay, so that is a process of how you done the determination of the enzyme activity. Okay, so is there any question about the experiment today? Ada soalan tak mengenai apa-apa yang awak perlu buat untuk eksperimen hari ini?
So far,